The analysis of rigid body motion must always be done in relation to a given frame of reference. A standard reference is represented by a set of space coordinate axes. This is, however, a pure mathematical concept. To facilitate the illustration and improve its physical meaning, let's attach the coordinate axes to a body in order to obtain a concrete reference system. Let's call it a physico-mathematical reference system. This allows the easy pictorial distinction between not accelerated and accelerated reference systems. To obtain the description of the dynamics of rigid bodies in terms of the classical mechanics, that is, applying Newton's laws of motion, the most appropriate reference system is the not accelerated reference. Better known as inertial reference system, one with zero net force acting on it and moving with uniform velocity, therefore one in which Newton's first law holds. Since the reference body does not interact with any other body, this system allows a complete description of the interaction of the bodies, both in linear and curvilinear interaction acceleration processes. The most fundamental state of a rigid body in space is when it is free of applied forces, thus not accelerating and therefore does not interact with any other body. It has been demonstrated, since Galileo, that in this situation a body is at rest or rectilinear uniform motion with respect to the not accelerated or inertial reference. Since a body does not interact with other bodies, rest and rectilinear uniform motion are, however, indistinguishable. The body can be at rest with respect to one inertial reference system and in rectilinear uniform motion with respect to another inertial reference with different velocity. In the universe, however, all bodies are immersed in a general gravity field, therefore moving in curved paths and accelerating all the time, changing the direction and or the magnitude of its velocity vector. Remember, we are talking in terms of classical mechanics, that is, in small regions of space and bodies at low speeds. In the general relativity theory, dealing with the universe at large, the bodies do not interact directly, but cause space-time to warp. As a result, all trajectories are curvilinear. This means that, strictly speaking, there isn't rest or rectilinear motion in practice, as well as concrete not accelerated or inertial reference systems. Despite its theoretical nature, the conceptual not accelerated or inertial reference remains as the necessary point of view to describe acceleration processes in accordance with Newton's laws of motion. A linear acceleration process is an approximation then in small regions of space or over a small portion of the surface of a planet, a place of our everyday lives, machines, transportation, etc. A prime example of symmetry in applied mechanics, any acceleration process always requires a pair of interacting bodies, under the action of a pair of equal and opposite applied forces. In addition, the bodies manifest upon each other an inertial resistance, allowing their reciprocal finite acceleration. In the curvilinear motion, the same acceleration conditions apply. When two bodies interact, the inertial resistance of each body to the bending of its path is manifested upon the other reciprocally. While the not accelerated or inertial reference system is conceptual, the accelerated or non-inertial reference is the only concretely available. The first type is the one that is accelerating in a straight path. The second type is the rotational reference. The third type moves in a curvilinear path at constant rotational speed, with the direction of the tangential velocity vector constantly changing, or varying the rotational speed with the magnitude of the tangential velocity vector also changing. For instance, consider a non-inertial rotational reference system with coordinate axes fixed to a body is attached to the center of a rotating disk. Suppose that a ball is placed on the disk, connected to the center shaft by a link. With respect to the non-inertial reference body attached to the center of the disk, the ball is at rest. Suppose the link is withdrawn, releasing the ball, whose behavior is described under the point of view of an external, not accelerated or inertial reference body. The ball, now free, moves in a straight path in accordance with Newton's first law. However, with respect to the rotating, non-inertial reference body at the center of the disk, the ball moves toward the disk rim in a curved path. Since a force is needed for a body to move in a curve, it is impossible to describe the curved motion of the ball with respect to this non-inertial reference using Newton's third law. In small regions of the surface of a planet, a reference system not accelerating with respect to that surface is used as an approximation of a conceptual inertial reference. The symmetry of any acceleration process with this approximation can be described using Newton's laws. However, using a non-inertial reference, accelerated at the same rate of the body, A, makes the body to be at rest with respect to this accelerated reference, compromising the explanation and appropriate understanding of the process dynamics, in terms of the effects of the applied forces and the resulting accelerations, making Newton's laws inapplicable. Two interconnected bodies, for instance, by contact under the action of a pair of equal and opposite forces, resist acceleration reciprocally in accordance with Newton's third law. Despite this arrangement, the reference body ultimately is physically non-inertial because that portion of the surface is moving in a curve with the surface of the planet. In many situations, the chosen reference body takes part in the acceleration process. In these cases, it is impossible to describe the acceleration process under the point of view of this non-inertial reference using Newton's third law. The symmetry and the dynamic interaction in all acceleration processes can be readily described using an external, conceptual not accelerated, or inertial reference body, especially when the center of mass of the system is not accelerating with respect to the inertial reference body. Let's now consider a ball and a non-inertial reference body released from the top of a tower to start an accelerated motion with respect to an external conceptual inertial reference system. During its accelerated motion toward the surface of the planet, the ball is at rest with respect to the accelerating non-inertial reference. With respect to this non-inertial reference system, the ball is at rest, therefore free of any applied force. Since the ball is at rest under the point of view of this non-inertial reference, it is impossible to explain the accelerated motion of the surface of the planet toward the ball. Gravitational phenomena is nowadays treated with the general relativity theory. The non-inertial reference body is released simultaneously with a system of two balls connected by a compressed spring. Under the action of a pair of equal and opposite forces, the resulting acceleration process, however, can be described using Newton's third law. With respect to the non-inertial reference, the center of mass of the system of the two connected balls is at rest with respect to this non-inertial reference, leading to the conclusion that the only forces acting on the bodies are the equal and opposite pair provided by the expanding spring, to cause the bodies to move in rectilinear paths. However, with respect to an external conceptual inertial or not accelerated reference system, the paths followed by the two balls are symmetric and opposite curves toward the surface of the planet. It is well known from Newton's first law that a ball placed on a disk will move in a straight path when the disk starts rotating. Now consider that, around the inner disk with a ball resting upon its surface, a rotating outer flat ring is installed to which a non-inertial reference body is fixed. When the outer ring rotates, with the attached non-inertial reference body while the inner disk remains stopped, the ball rotates freely with respect to the non-inertial reference body, and its motion cannot be explained with Newton's third law, since the necessary forces cannot be identified as well as the required interaction. Another problem with non-inertial reference systems is seen in the popular representation of the rotation of a body around a fixed center axis or central body. If the motion of the body, A, described under the point of view of a rotating reference attached to the central body, with respect to which the ball is seen as being at rest. If the reference body attached to the central body is not rotating, the central body is seen as being at rest, therefore without any force acting on it, while the body, A, rotates in a circular path. Since the body, A, tends to move in a straight path in accordance with Newton's first law, it must be subjected to the action of a centripetal force with origin in the central body. Since the central body is at rest with respect to the attached reference, its inertia must be infinite and the circular motion of the body, A, contradicts Newton's third law. To fully explain the situation, the process has to be described under the point of view of an external, conceptual inertial or not accelerated reference body. Now we have a system of two interacting bodies, the central body and the body A. The two bodies rotate around the center of mass of the system, which show the symmetry of the acceleration process according to Newton's laws. Observing the two bodies in motion rotating around the center of mass of the system, one can clearly identify the reciprocal manifestations of the inertial resistance of the two bodies against the bending of their paths acting upon each other as equal and opposite centripetal forces. Now in complete accordance with Newton's laws of motion. This same approach can be applied to the unbalanced rotation. The unbalanced rotation is usually considered in a restricted process in which the rotating system is attached to a structure or the surface of the planet, a process that results in vibration. The interest here is in a system free in space. Under the point of view of an external, inertial reference system, a motor or central body and the body, A, rotate around the center of mass of the system. In conclusion, the not accelerated or inertial reference system is the most appropriate reference to fully describe acceleration processes with the application of Newton's laws of motion. In a universe where all bodies move in curvilinear paths, however, this inertial reference, in broad sense, does not exist concretely. The description of interactions and resulting accelerations of rigid bodies in terms of Newton's third law can only be approximated in very small regions under certain conditions. Only accelerated or non-inertial reference systems are concretely available that causes misinterpretations, conflicting with Newton's laws. With these reference systems, in many situations, some accelerations disappear.